Hi everyone, and welcome to this course in calculus. Today, being the first lecture, we will introduce the set theory, its notation, and some definitions. This course is for those who are attending or willing to attend maths at the university, those who are attending last years of high school, or simply those who want to learn math in a precise fashion, and in specific, calculus. So, let's start with an introduction to the set theory. First of all, we have to define a set, which is a collection of objects viewed as a single entity. The sets are identified by capital letters, so A, B, C, D, P, Q, X, Y, and so on. Instead, the elements of a set are denoted then by lowercase letters. So in this case, A, B, C, F, X, P, S, and so on. Some example could be the set A, whose elements are F and G, the set B, whose elements are F, M, and G, and eventually the set C, whose elements are G, F, and G again. Now, the notation F belongs to A, written in this way, means that F is an element of A. If we want to indicate an element which is not inside A instead, we write like this. So M is not an element of A. Further example in numbers could be the set E, composed by the elements 1, 2, 3, 4, and 5. The set F, composed by 1, 3, and 5, which is the set of odd positive integers less than 7. And G, composed by 2, 4, 6, 8, 10, and so on, which is the set of positive even integers. The three dots stand for and so on, and it can be used only when the meaning is clear, as in this example. We can move now to some definition, which relates the sets. The first definition that we have is the one of set equality, and we say that two sets x and y are equal if and only if all the elements of x are also all the elements of y. In more precise and formal way, we can write that x is equal to y if and only if, which is represented by this double arrow. Whenever a generic element of A belongs to x, this condition, then this generic element A also belongs to y. And furthermore, for each generic element B belonging to y, then this element B belongs also to x. So when this condition is not met, meaning that if x has an element not contained in y, or vice versa, if y has an element not contained in x, then we say that x is different from y, and we can denote it by this notation, so different. We can have also two observations. The first one is that the order does not matter. In fact, if we have a set I composed by 2, 5, and 8, and a set H composed by A, 2, and 5, then I is equal to H by definition. The second observation instead is that repeated elements are not a source of complexity, in the sense that if we have a set where an element is counted twice or more than 2 times, then it's still considered as one object when we want to relate two sets. In fact, if we want to look at the set A and C, we see that A has elements F and G, while C has element F and G counted twice, but by definition they are equal, so it's still all that A is equal to C. In fact, each element that is contained in A is also contained in B, and each element contained in B is also contained in B. If we want to relate instead the sets A and B, we can observe that F and G both belong to A and B. So we have F, we have G, We have F and G, so they both belong to the both sets. But M does not belong to A, meanwhile it belongs to B. So this can be written as B has an element and not contained in A. If we look at the definition of set equality, we can see that if a set, in this case, has an element not contained in Y, then we can say that these two sets are different. And this is exactly the case here. So we can write that A is different from B. We can now introduce the definition of subset. In fact, it's possible to form new sets from existing ones, and they are called subsets. If we have two sets, X and Y, X is said a subset of Y if each element of X is also an element of Y. In fact, it is possible to form new sets from existing ones, and these are subsets. If we have two sets, X and Y, then X is said to be a subset of Y if each element of X is also an element of Y. And more formally, it can be written as for each A. So for each is denoted by the symbols, where A is a generic element. Then if A is an element of X, if A belongs to X, also A belongs to Y. If this holds, then we can write that X is a subset of Y. The second definition that we can have from this definition of the subset is that if X is a subset of Y and if Y is a subset of X, so if in both ways we have subset, then X is also equal to Y. This is an if and only if. In fact, if X is equal to Y, then X belongs to X is a subset of Y and Y is a subset of X, and vice versa. Means that X is equal to Y if and only if X is a subset of Y and Y is a subset of X. It's important to bear in mind. At this point, we can recycle the example from before and see what are the relationship between the sets. We now want to relate the sets A and B. All the elements of A are also elements of B, meaning that A is a subset of B. Looking at B instead, not all the elements of B are elements of A, meaning that B is not a subset of A. Hence, A is different from B. If we want to relate instead the sets A and C, all the elements of A are also elements of C, so G and F, meaning that A is a subset of C. And all the elements of C, G, F, and G, are also elements of A, so that C is a subset of A, and we can conclude that A is equal to C. When we have this condition, we say that A and C are improper subsets. We can now go on. In fact, a subset or a set can also be identified by means of a property. More formally, we can write that a set U is defined by all the elements X such that X satisfies some properties. We have already defined sets by means of property, and in fact, here F and G are sets where the first one, F, is the set where the first property is that they must be odd positive integers, and the second property is that all the elements must be less than 7. Meanwhile, for the set G, the property is that we have to have only positive even integers. So we can do other examples, such as the set M, where all the elements are multiple of 3 and there are less than 10. We can write the set together, so this is equal to the first rule property is that it must be a multiple of 3, so we can have 3, 6, 9, 12, 15, and so on. But the second property tells us that it must be less than 10, so that 12 and 15 does not count, and also the higher numbers. So that eventually this set is the set composed by 3 elements, which are 3, 6, and 9. In this way, it's possible to specify also set with infinite elements, such as S, whose element y are greater than 6. And this is the set 7, 8, 9, 10, and so on. The letters x, m, y are just dummy variables, meaning that we can use whatever letters we want. In fact, here S can also be written as the set L such that L is greater than 6, or the set P such that P is greater than 6, and so on. Another important concept is the empty set. In fact, a set which has no elements is called an empty set. So if A has no elements, then A is equal to the empty set and is denoted by this symbol. The last property of sets is that each set has as a subset the empty set and also the set itself. So if X is a generic set, then the empty set and X, they both are subset of X. Thank you for listening. This is the end of the lecture, and in the next one we will talk about union, intersections, and complements. If you have any question, just text me in the comment below. Bye bye. See you in the next video.